Let me begin with the introduction. The disposal of tea rosea leaf biomass poses environmental and economic challenges. High moisture content make it difficult to store, transport, and use in industry like biofuel production. Traditional drying methods are slow and inefficient, which add to the problem. Ultrasonication, which use high-frequency sound wave, offer a promising solution. It can speed up drying by improving heat and mass transfer. However, its effect on the moisture content of tea rosea leaf have not been fully explored. In this study, we aim to test how ultrasonication at different temperature and duration affects the moisture content of this leaf. We believe the higher temperatures and longer treatment will reduce moisture more effectively. Let's look at some studies related to ultrasonic treatment. Ultrasonic use high-frequency sound wave to impact moisture content by improving mass transfer and speeding up processes. According to Yang et al., ultrasonic testing is a non-destructive method used to check material structure. It works by adjusting sound wave setting for accurate result. Another research from Su and Kovaco Paul et al., ultrasonic bath creates small bubbles producing heat and reactive particles. This improves moisture removal and make the process more efficient. The other research from Pan et al., researchers are also use ultrasonic wave and material density to predict and model moisture content, showing that this method works well for reducing moisture. This study showed the ultrasonic is a promising tool in managing moisture, which is why we are applying to tea rosea leaf. Let's look at some previous study related to ultrasonic bath. Research by Astrofi et al. Showed that ultrasonication improved the properties of material. For example, it enhanced the mechanical strength, water resistance, and film formation of tea rosea leaf. It makes the material more useful for various applications. Ultrasonic is also helpful in process like gelatinization. It helps evenly distribute fiber in starch, creating a stronger and more compact structure. Another study by Polen-Coitin et al. Found the ultrasonic bath with distilled water are great for cleaning surface after eating. This method even improved the bonding strength of resin. Let's review some studies about dried tea rosea leaf. According to Pagaza-Straffan, tea rosea leaf have many medical use, especially in South Mexico. They are used to treat respiratory issues, stomach problem, fever, diabetes, and parasitic infection. The extract also have hypoglycemic, antioxidant, antibacterial, and anti-cancer properties. While according to Tan et al., as a urban tree, tea rosea provide ecological and social benefit by improving green space in city. Another study by Devika, when dried, the leaf can be used to produce activated carbon. They also contain important phytochemicals like flavonoid, alkaloid, terpenoid, and polyphenol. These compounds are usually extracted using solvent in ethanol, petroleum ether, and water. Managing the moisture content of the leaf is essential to improve the extraction of these medicinal compounds. So for the biomass of moisture, according to Pedro and Zinker, moisture content is a key factor that affects the energy value and handling of biomass. High moisture levels can cause problems like self-heating in storage parts, which is increase the risk of fires. Another study from Jing Yu, for combustion, low moisture content improve energy density and burning efficiency. While high moisture leads to energy loss as water evaporates, controlling moisture also helps reduce pollutant emission, making energy production cleaner. Proper moisture management method such as drying, blending, or pre-treatment enhance biomass energy density, reduce pollution, and ensure safer and more sustainable energy production. Last but not least, according to Jingyu, one method of LIDAR-based technology which offer a quick and accurate way to monitor moisture content. This technique help improve energy efficiency and reduce emission in biomass power plant. Another study from Huang, another method is ultrasound pretreatment by using sound wave. It creates small channels in biomass tissues, making it easier for water to escape. This reduces drying time by 30 and 58% for products like apples, carrots, and can increase drying rates by up to 5 times. Both methods show how effective controlling moisture content can be, and ultrasound pretreatment in particularly could be valuable for our study on tea rosea.
Next is methodology. We have 4 methods that we use in this experiment. First, sample preparation. Next is ultrasonic treatment. Third is measurement of moisture content. And lastly, analysis of result. As for the sample preparation, the tea rosea leaf was being collected, remove the impurities by washing them with water, cut them to a small size, and dry them in the oven at 150 Celsius for 12 hours. Then by using a grinder, the leaf will be ground into a powder and stored it inside the cap bottle for the next analysis. Next is ultrasonic treatment. The tried sample were being mixed with distilled water at the ratio 1:20, and the mixture were placed in an ultrasonic bath filled with water at different temperature, which is 30, 40, and 50 Celsius in different time, which is 10, 20, and 30 minutes for each sample. Third is measurement of moisture content. After the ultrasonication, the sample will be dried again in the hot air oven at 105 Celsius until they reach a constant weight, and calculate them using the formula given. Lastly is the analysis of the result. The moisture content of the mixture of the Rosea leaf were being calculated before and after the ultrasonication treatment. To make a comparison, we look at the first question: how to treat the tea Rosea leaf via ultrasonication process. To treat the leaf using ultrasonication, first dry and grind the leaf into a fine powder to increase surface area. Second, choose an appropriate solvent like water, ethanol, or methanol based on desired compound, and use a solid to liquid ratio of around 1:20. Then place the powder leaf in a container with solvent and set up an ultrasonic bath, ensuring proper immersion, and adjust parameters such as amplitude, pulse cycles, and duration, while maintaining a low temperature to prevent degradation. After sonication, filter the mixture to separate solid from liquid extract, which can then be concentrated if needed. Store the extract in a glass container at low temperature to preserve its bioactive compound. This method enhances extraction efficiency by disrupting cell wall and improving mass transfer through cavitation. We move to the next question: how does the ultrasonication treatment affect the moisture content in the sample? Ultrasonication treatment affect the moisture content in sample by enhancing drying rates and facilitating moisture removal. Study indicate that ultrasound pretreatment can significantly reduce the drying time of material by increasing the rate of moisture loss during the drying process. For instance, when applied to eucalyptus and other materials, ultrasound increased drying rate by 5 to 28% depending on the initial moisture content and treatment duration. This improvement is attributed to the cavitation effect produced by ultrasound, which create microchannel in the material, thereby reducing resistance to moisture diffusion and promoting faster water migration. Additionally, ultrasound alters the internal structure of the sample, leading to a more effective redistribution of water within the cell, which further accelerate moisture removal during drying. Overall, ultrasonication serves as an efficient method to decrease moisture content in biological material while enhancing their drying characteristics.
The result of data ultrasonic treatment after, before, and the ultrasonic bath. The data divided into three temperatures is 40 Celsius, 50 Celsius, and 60 Celsius. Also, each temperature is split into three categories in time: minute, 10, 20, and 30. Based on the data result, it shows the effect of different temperature in mass biomass using the ultrasonic bath at 40 Celsius. 2.003 gram decrease the mass to 1.9135 gram. After 10 minutes in 20 mass, the mass continued to decrease to 1.9021 gram, but in 30 minutes, the mass increased again to 1.931 gram. At 50 Celsius, the mass in 2.0225 gram decreased to 2.002 gram after 10 minutes and continue increase to 2.022 gram after 2 minutes. But after 3 minutes, the mass decreased into 2.00 gram, and at 60 Celsius, 2.004 was decreased to 1.9542 gram after 10 minutes and continued decrease after 2 minutes, which was 1.927 gram, and increased the mass to 1991 after 30 minutes. That one show the percentage of yield in x-axis. It shows temperature using an ultrasonic bath, while using in y-axis show the percentage of yield. The data is shown the higher percentage of in 50 Celsius for 30 minutes it is 99.17%, and the continue for 60 Celsius in 30 minutes it is 99.65%. For the lower percentage of the 40 Celsius in 20 minutes it is 94.99%. Based on the data is represent the percentage of yield. Most of them is 90% because the effect of ultrasonic does not chemically affect the reaction. The ultrasonication has given me more impact on physical properties. Table 2 shows the result of the moisture content percentage after the ultrasonic bath. By using the standard method, moisture content ASTM is 1756010
2020, the data divided into three temperatures is 40 Celsius, 50 Celsius, and 60 Celsius. Also, each temperature is split into three categories. In time is 10, 20, and 30. In table, show at 40 Celsius is started is 5.16% for 10 minutes, continue decreasing to 4.16% for 20 minutes, but in 30 minutes increase into 5.12%. At 50 Celsius, it shows the percentage is lower than at 40 Celsius. It is 1.52% for 10 minutes, is 1.51% for 20 minutes, and for 30 minutes is increased to 2.52%. At 60 Celsius, a small increase into 2.85% for 10 minutes and continue increasing into 4.59% for 20 minutes and 4.71% for 30 minutes. Based on the result, I was able to identify the higher percentage of moisture content in 40 Celsius in 30 minutes and the lower percentage of moisture content in 50 Celsius in 20 minutes. Discussion, we are focused on key finding is exchange biomass suitability by reducing moisture content, improving combustibility, and enabling biofuel conversion. Next is support waste management by reducing wood waste from industries such as construction, agriculture, and landscaping. And lastly, contribute to sustainability by reducing greenhouse gas emission and replacing fossil fuel. Secondly, implication is ultrasonication primarily reduce particle size, forming emulsion, but minimally impact moisture content chemically. It is because ultrasonic bursts focus more on physical rather than chemical properties. For example, higher yield percentage observed due to particle size is a limitation. Limitation have a two is ultrasonic burst handling error may influence result, and filtration method impact is manual filtration less accurate than vacuum filtration. For example, in result varied at 40 Celsius and 50 Celsius in table 1. Lastly, for application is sustainable circular economy is biomass converted into energy or bio-based product. Then high quality woody biomass production.
Conclusion, ultrasonic treatment showed promising for reducing moisture in tea rosea leaf, particularly at higher temperature. It had minimal impact on the overall biomass yield. This suggests that ultrasonic treatment could be a value technique for preparing biomass for various applications such as biofuel production. Future research with larger sample size and controlled conditions is necessary to further optimize the process and fully understand its potential.